After studying this module, you shall get an introduction about heteroscedasticity and shall be able to understand the various remedial measures of heteroscedasticity. Next, it will discuss the use of various remedial measures in detail and the need and applicability of the various remedial measures. Slide 9. This diagram represents homoscedasticity, one of the assumptions of classical linear regression model. The ordinary least squares estimators are BLUE under this condition.
Heteroscedasticity is a result of a data generating process that draws disturbances for each value of the independent variable from distributions that have different variances. It also implies that dispersion of the dependent variable around the regression line is not constant. Heteroscedasticity usually arises in cross-sectional data where the scale of the dependent variable tends to vary across observations and in highly volatile time series data. It is less common in other time series data where values of explanatory and dependent variables are of similar order of magnitude at all points of time. A standard manifestation of heteroscedasticity is that the spread of actual values around the linear regression line will not be constant. Also, the plot of regression residuals against, say, the predicted y values will exhibit some characteristic pattern instead of being random. A standard manifestation of heteroscedasticity is that the spread of actual y values around the linear regression line will not be constant. Also, the plot of regression residuals against, say, the predicted y values will exhibit some characteristic pattern instead of being random.
This diagram represents homoscedasticity, one of the assumptions of classical linear regression model. The ordinary least squares estimators are BLUE under this condition. Heteroscedasticity is a phenomenon where the stochastic random disturbances exhibit a non-constant conditional variance. It is a violation of one of the assumptions of the classical linear regression model. It occurs when the disturbance term Ui of all the observations have a non-constant conditional variance. It may be a result of specification errors or data issues, and it may be anticipated in most regression models with the cross-sectional data, especially in cases where the scale of dependent variable varies across the observations. It can also be observed in highly volatile time series data. This diagram represents heteroscedasticity. It occurs when one of the assumptions of classical linear regression model is violated. In the presence of heteroscedasticity, ordinary least squares estimators and forecasts based on them are still unbiased and consistent, but lose their BLUE property. The estimated variances and covariances of the estimators are biased and inconsistent. Hypothesis testing procedures and statistical inference do not remain valid any further. Hence, if the OLS method is used to estimate the parameters and to test the hypothesis for a data suffering from heteroscedasticity, then we are likely to get misleading conclusions. This makes necessary to find some remedial measures to solve for the heteroscedasticity problem. The unbiasedness and consistency properties of the OLS estimators remain intact even after heteroscedasticity. But they are no longer efficient, not even asymptotically, that is, large sample size. This lack of efficiency makes the usual hypothesis testing procedure of dubious value. Hence, the remedial measures are needed.
After understanding the basics of heteroscedasticity, its impact on estimators, detection methods, and need for remedy, dear students, it is now important to understand what different remedial methods of heteroscedasticity are available. It is also important to understand what form do these remedial methods of heteroscedasticity take and how are they used. As in the presence of heteroscedasticity, estimators lose their blue property, which also means that ordinary least square estimators can no longer be used as the assumptions of the classical linear regression model are violated. It therefore becomes important to rectify. There are various methods available which can assist in rectifying heteroscedasticity. These measures can be classified into two categories. First category includes remedial measures when true error variance is known, which include generalized least squares and weighted least squares WLS estimator as the most popular ones. The second category includes remedial measures when true error variance is unknown, which include techniques like feasible generalized least squares or known as FGLS estimator, White's correction and plausible assumptions about heteroscedasticity pattern, among many other commonly used techniques. A few facts that might interest you about each of these techniques and otherwise are as follows. The term heteroscedasticity means differing variance and comes from Greek hetero, which means different, and scadesis, dispersion. While the influential 1980 paper by Hulbert White used the term heteroscedasticity rather than heteroscedasticity, the latter spelling has been employed more frequently in later works. The econometrician Robert Engel won the 2003 Nobel Memorial Prize for Economics for his studies on regression analysis in the presence of heteroscedasticity, which led to his formulation of the autoregressive conditional heteroscedasticity, or known as arch modeling technique. GLS was first described by Alexander Atkin in 1934, a special case of GLS called weighted least squares. FGLS is preferred over OLS under heteroscedasticity or serial correlation. However, if classical assumptions of OLS are met, then least squares may be more efficient than FGLS. Another important fact is that the alternative names of White's correction are Huber-White's standard errors, Eicher-White, or Eicher-Huber-White. Heteroscedasticity consistent standard errors are used to allow the fitting of a model that does contain heteroscedastic residuals. The first such approach was proposed by Huber in 1967, and further improved procedures have been produced since for cross-sectional data, time series data, and gauge estimation. From here on, we will discuss each of these methods and quote a few examples to create a better understanding of how these methods are used to rectify heteroscedasticity. Students, now as you are familiar with the basics of heteroscedasticity, we proceed to its remedial measures. First, we begin the discussion on the remedial methods of heteroscedasticity, which are followed when true error variance is known, which includes generalized least squares and weighted least squares WLS estimators as the most popular ones. All this and many other details will be discussed from here on.
There are various methods available which can assist in rectifying heteroscedasticity. These measures can be classified into two categories. First, remedial measures when the true error variance is known, which include generalized least squares and weighted least squares estimator as the most popular ones. Second, the remedial measures when the true error variance is unknown, which includes techniques like feasible generalized least squares estimator, White's correlation, and plausible assumptions about heteroscedasticity pattern, among many other commonly used techniques. From here on, we will discuss the remedial methods of heteroscedasticity when true error variance is known, which include generalized least squares and weighted least squares estimator as the most popular ones. This category is of great relevance because it's not always possible to obtain the true error variance for a study. Let's discuss each one of them in turn. If the variance of the error term is non-constant, then the best linear unbiased estimator is the generalized least squares estimator. It is also called as weighted least squares estimator. To understand it better, consider the following general linear regression model with heteroscedasticity. This model has two independent variables and the variance of its error term is given by sigma square. Now to derive the GLS estimator for this model, first find the error variance sigma I square and take the square root of the error variance sigma I. This gives the standard deviation of the error. Then divide every term on both the sides of the regression equation by this standard deviation of the error, that is sigma I. This gives the following regression equation with a new transformed model. The equation 1 represents the entire model has been divided by sigma, where sigma is the weight. Here, it is important to note that the error variance for the transformed model is variance mu I is equal to variance mu I divided by sigma I equal to variance mu I divided by sigma I square, which is equal to 1, which is a constant. Therefore, the transformed model has a constant error variance. It satisfies all the assumptions of the classical linear regression model. Now we can apply the OLS estimator to the transformed model. This method of applying OLS estimator to the transformed model is called the GLS estimator. That is, run an OLS regression of y star on x1 star, x2 star, and x3 star. Note that the transformed model does not include an intercept term in the regression. The weighted least squares estimator is the OLS estimator which is applied to a transformed model after multiplying each term on both the sides of the regression equation by the weight, denoted by Wi. For instance, consider the following general linear regression model with heteroscedasticity. This equation states that the general linear regression model and the variance of the error term is given by the sigma square. Now, if Wi is equal to 1 divided by sigma I, then we get the GLS estimator. Thus, the GLS estimator is identical to the weighted least square estimator. Or one can say that the GLS estimator is a particular kind of WLS estimator. In GLS estimation, a weight Wi is given to each observation of each variable, which is inversely proportional to the standard deviation of the error term. It implies that the observations with a smaller error variance are given more weight in the GLS regression, and observations with a larger error variance are given less weight.
Students, as you are now familiar with the basics of weighted least squares estimator and know how to use them, it is time to take up an example and get a better understanding of weighted least squares estimator. Through this example, we want to study the relationship between compensation and employment size for a firm. All this and many other details would be discussed now.
In order to illustrate the method, suppose we want to study the relationship between the compensation and the employment size for the data represented in the table 1. We measure the employment size by various intervals such as 1 to 4 employees, 5 to 9 employees, and 1000 to 2499 employees, etc. for simplicity. Y represents the average compensation per employee and X is the employment size. Using any software package, we can easily run the WLS regression using sigma I as the weight. The WLS regression with sigma I as the weight will make the estimators BLUE and remove heteroscedasticity. But this method is not free from limitations. The main problem with GLS estimator is that the true variance and the standard deviation of the error for each observation in the sample is unknown and unobservable. Thus, the GLS estimator cannot be relied upon and hence becomes an infeasible estimator.
Students, as of now, you have become familiar with remedial measures when true error variance is known, which includes GLS and WLS estimators. Now we move from known error variance to unknown error variance. The remedial measures when the true error variance is unknown include feasible generalized least squares FGLS estimator, White's correction, and plausible assumptions about heteroscedasticity pattern. These methods are important because it is not always true that the true error variance is known. We will study them in depth now.
Remedial measures make an implicit assumption that the true error variance is known. However, in reality, it is difficult to have knowledge of the true error variance. Thus, we need some other methods to obtain consistent estimate of the variance of the error term. White's heteroscedasticity, consistent variances, and standard errors method shows that the statistical inferences can be made about the true parameter values for large samples, asymptotically valid. It develops a method to obtain consistent estimates of the variances and covariances of the OLS estimators. It is also called as heteroscedasticity consistent covariance matrix HCCM estimator. For instance, consider the following regression model. The variance is not known. Hence, White suggests to use as an estimate of true population variance. According to White, equation 2 is a consistent estimator of equation 1, or the equation 2 converges to equation 1 as the sample size increases indefinitely. Hence, White's heteroscedasticity corrected standard errors are also known as robust standard errors. In this method, we use the sample data to obtain an estimate of the sigma t, and then apply the GLS estimator using the estimates of sigma t. When we do this, we have a different estimator called the feasible generalized least squares estimator, or the FGLS estimator. To obtain this FGLS estimates of the parameters beta 1, beta 2 and beta 3, following steps should be taken. First, run the original OLS regression and obtain the residual. Second, square these residuals mu I square hat and regress it on a constant xi2 and xi3 by using the OLS. Then use the estimates of alpha 1, alpha 2 and alpha 3 in order to calculate the predicted values of sigma t square hat. This gives an estimate of the error variance for each observation. Since we cannot have negative variance, any predicted value that is non-positive must be replaced with the squared residual for that observation. In the last step, take the square root of the estimates of the error variance sigma t hat for each observation. Find the weight Wi is equal to 1 divided by sigma I hat for each observation. Multiply yi, xi2 and xi3 for each observation by this weight. Finally, regress wi yi on wi xi2 and wi xi3 using OLS. It is important to note that if the transformed model of heteroscedasticity that we get after using the FGLS estimator is a reasonable approximation of the true heteroscedasticity, then the nonlinear FGLS estimator is asymptotically more efficient than the OLS estimator. However, if it is not a reasonable approximation of true heteroscedasticity, then the FGLS estimator will produce worse estimates than the OLS estimator. Suppose we collect a sample of 50 states of US on per capita expenditure on the public schools by a state in 1979. It's denoted by Y, and per capita income of the state in 1979. We get the following regression results. From this regression result, we see that the White's heteroscedasticity corrected standard errors are considerably larger than the OLS standard errors, and hence the estimated t-values of the White's heteroscedasticity are much smaller than those obtained by OLS. Thus, we find that the OLS estimates are statistically significant at the 5% level. However, on the basis of white estimators, they are not statistically significant. Therefore, it is very important to use White's heteroscedasticity test and comparing it with his OLS output as to check to see whether heteroscedasticity is a serious problem in a particular set of data. In this method, we need to make some assumptions about the true error variance and transform the original regression model. After transformation, the new model satisfies the homoscedasticity assumptions. Let's say original regression model is yi is equal to beta 1 plus beta 2 xi2 plus beta 3 xi3 plus mu I, and the variance of the error term is sigma square. Under plausible assumptions about heteroscedasticity pattern, there are four possible cases, namely case 1 when the error variance is proportional to xi, case 2 when the error variance is proportional to x squared, case 3 when the error variance is proportional to the square of the mean value of y, and case 4 the log transformation. We will discuss each one of them from now on. Run the original OLS regression and obtain the residuals. Plot the square of these residuals against the explanatory variable x. If we get a similar pattern to figure 1, then we say that the error variance is proportional to or linearly related to and is the factor of proportionality, which is a constant. Run the original OLS regression and obtain the residuals. Plot the square of these residuals against the explanatory variable x. If we get a pattern similar to figure 2, then we say that the error variance increases proportional to xi. Now we transform the regression model by dividing the original regression equation by xi, and we can show that the error term vi is homoscedastic, and hence we can use OLS method to produce the BLUE estimators. According to this assumption, the error variance is proportional to the square of the mean value of y. Now we transform the original regression model and we get the variance, which is a constant. We can now show that the error variance Vi is homoscedastic. A log transformation of the original regression model can help to reduce the problem of heteroscedasticity. It has many advantages, like it reduces the scale of measurement of variables by reducing a tenfold difference to the twofold difference between the values. Secondly, it represents the elasticity of y with respect to x, that is, the percentage change in y for a percentage change in x, whereas in the original model it represents the change of y for a unit change in x. However, we find some problems associated with this transformation method. In multiple regression models, we may not decide which of the x variables should be chosen for transforming the data. Log transformation is not applicable if some of the y and x values are 0 or negative. It may happen that the ratios of variables are found to be correlated even though that the original variables are uncorrelated or random. When the variance is unknown and estimated by using one of the above mentioned transformations, then all our testing procedures using the t-test F-test, etc. are valid only in case of large samples. Therefore, one must be careful in interpreting the results based on the various transformations if the sample size is small. To summarize, heteroscedasticity means unequal variance and is a violation of the assumptions of classical linear regression model. When it occurs, the estimators no longer remain BLUE, and hence we require remedial measures. We discussed various remedial measures which were classified into categories of known true error variance and unknown true error variance.
My dear students, now you must have understood all about heteroscedasticity, the different diagnostic tools to detect the presence of heteroscedasticity, and the remedial measures well in detail. This module familiarized you with the concept of heteroscedasticity, and it also taught remedial measures. These measures are classified into two categories. Remedial measures when the true error variance is known. Within this category, we studied GLS, that is generalized least squares, and weighted least squares WLS estimator. The other category is remedial measures when true error variance is unknown. Within this category, we studied feasible generalized least square estimators and White's correction. And third is plausible assumptions about heteroscedasticity pattern. Although this knowledge is not exhaustive and many more elements are yet to be discovered, therefore it is suggested that you study them in detail.